Now, let us look at again closely what happens in the internal forces. If I take a small element like this, what we see here, and this is a region which is subjected, it's a simply supported beam which is subjected to an uniformly distributed load like this, and close to the region I am going to have shear, high shear force, but bending moment is going to be less. Let us take that the bending moment is, I am taking a section very close to the support, let us say that bending moment is not much. If I am looking at an element at the neutral axis, you know that it is going to be subjected to only pure shear, right. So, if you take this cross section, again we have seen this in the previous, right. So, for this cross section, rectangular cross section, my bending stresses are going to be like this, right. I am going to have compression, tension, these are normal stresses. Now, shear I am going to get this kind of a distribution. Now, if I am taking an element at this point, you see here this tau v, we have seen that it is going to be 3 times of tau average in the previous slide, right. So, this element if I am taking right at the neutral axis, normal stress will be 0, only you will have shear stress. Now, you know the Mohr circle, I can convert this into principal stresses like this, right, at about, for when an element is subjected to pure shear, principal stresses will be, or principal planes will be at an angle 45 degree, right. So, we know how to get all this principal shear stresses. So, you see here, if I draw an angle, so you are going to have an element, if I, if I look at the plane at 45 degree, you will have principal compression and principal tension like this. And so, any state of shear or the combination of shear and normal stress can be converted into principal stresses. You know that is the principle of, using principle of Mohr circle, we can convert them into an principal stresses. Now, if you draw the principal stresses, again you know how to draw the principal stresses. In the vertical axis we take shear stress, in the horizontal axis we take the normal stresses. Now, this element, if you look at the stress state, here normal stress is 0, this is, let us say, clockwise shear is, if I take positive, plus tau and 0 here, I plot this point, I plot in the next plane. So, we look at the stress state in the 2 orthogonal planes like this and then plot them. I got 2 points, origin is given to you, so you can draw the circle and you know how to do the Mohr circle. So, you see here for pure shear, the circle will be exactly concentric with respect to the origin, and if I keep increasing my shear demand, the circle will keep growing in size. Now, if I keep increasing my shear load, now principal stress can reach my principal tensile stress, that means the minimum principal stress can reach the tension strength. Here I am taking tension as positive, so sigma 2. So, it is going to reach tension and then it is going to crack. Okay. Now, if you look at in pre-stress, let us see what is happening. Okay. So, the same element, this is an RCC beam, right. Now, this is in pre-stress beam. Okay. Now, let us look at what is happening. In pre-stress, you know that I am going to apply a pre-stressing force like this at an eccentricity, some eccentricity E. Now, if the same element is taken at the neutral axis, now what would be the stress state? Now, here there is a pre-stress, so P is going to be greater than 0 if I take compression is positive. So, in this plane, now I will have a normal stress plus the shear. In this plane, I do not have any vertical stress, I will have only shear stress. So, for this one, if you plot your Mohr circle, you will find that the principal compressive stress plane will make an angle which is less than 45 degree with respect to horizontal, right. So, that is the reason if you look at this crack will follow the principal compression direction, because principal tension is perpendicular to the principal compression. So, if I have to, how this element will crack, for example, it will be cracking perpendicular to the tension. So, it will crack like this. So, that means the crack will follow the principal compressive stress trajectory direction. So, and if you find that, so this alpha, if I take it, or let us say this is theta, is going to be less than 45 degree. Here if we take this theta, it will be equal to 45 degree. So, what does the prestressing does? The prestressing is going to make the crack angle shallower than what you have it in reinforced concrete. So, that is what we are trying to see, and we can explain this using Mohr circle also. So, you plot these two stresses, right, and then you get this, and then you can calculate your principal compression and principal tension, right. So, what the circle is doing is, because of the virtue of your compression, which I have taken it as negative, basically the circle gets shifted towards left. That means it is going more towards compression side. So, that means in other words, now the same beam will be able to take more shear force or shear load before it is going to crack in tension, right. So, that is what it is. Now, let us look at what are the differences in internal forces between reinforced concrete and prestressed concrete. And you see, this is a cable that I have, and I have taken this, let us say I have a beam like this again, which is simply supported and which is subjected to some load which is capital W. And the blue color curve, what you see is a prestressing cable. This is a prestressing cable. The prestressing cable, and it is having some profile. Now, if I take the small elemental length dx and I look at what are the state of internal forces that you have, we know that I am applying tension on the cable, but I am looking at what is the effect on the concrete. So, concrete it is going to be subjected to some compression force like this. This is the cable profile, this is the cable. Okay. We are looking at what is the effect of the cable on the concrete. If I take the small elemental length dx, where the slope of the cable is not going to change much, I am again going to assume constant like this. So, this is the cable angle which is alpha x. So, you see here there is going to be, if I resolve this compression, I am going to have again a vertical component and a horizontal component. Now, let us look at what is that I am going to get. So, you see here in prestress, if I look at it, I am going to have, this is the shear, okay, shear from loads, this is shear from loads. In addition to the shear from the loads, I am also going to have some Py and Px. Px does not matter because we are looking at what are the forces on the vertical direction. So, there is going to be a Py, a vertical component of prestress, that is also going to act in this section. Either you take it this way or this way it is going to be Py and this is Px. So, what is the net shear that is acting? V net is going to be V from load minus Py. In either direction you look at it, V load and Py will be acting in opposite to each other, right. So, we can see that in a section, if you take the small element, that is what we are seeing here, this is load and this is prestressing. In this side, if I take, this is the shear from the load and this is the shear from the Vp component. So, either you take on the left side of the section or right side of the section, the net effect is there is a vertical component that is reducing the shear demand, okay, that is what we are happening. But in RC, in reinforced concrete, this Vp is 0 because there is no prestressing involved. So, what we can see is in prestressed concrete again, this vertical component is Py is nothing but P sin alpha, that is what we are writing here is a vertical component. Now, if alpha is higher, you know that the Vp is going to be higher. Similarly, when P is higher, again Vp is going to be higher. So, in this way, by controlling the amount of prestress and the angle of the cable profile, I can actually reduce the net shear demand in the cross section. So, we can write that in RC you have reinforced concrete, you have only shear from loads, you do not have this P sin alpha. So, what we can conclude from here is the shear demand in a prestress section for the particular load configuration will always be lesser than that what you have for a reinforced concrete. Okay. So, we can say shear demand is going to be lesser in prestressed concrete section and the crack angle is going to be shallower in prestressed concrete. That means it is going to result in a more economical design of stirrups, and mode of failures in shear deficient pre-stressed concrete beam is also going to be somewhat different than what you have for a reinforced concrete, because now the crack angle is different and you have pre-compression. So, that is going to change the way that beam is going to fail in shear. So, all these things we have to keep in mind in terms of pre-stressing and their beneficial effects on concrete behavior. Okay. Now, let us explain this through an example. What is the effect of pre-stressing? I am taken this 10-meter span, and let us say that the beam is subjected to 8 kilonewton per meter including self-weight, and the section that I have chosen is a very small cross section of 100 mm by 300 mm. Now, we want to compare for 4 different cases and calculate what is the principal tension that will be developed at the support location. So, basically at the location of here, maximum shear location, I am going to look at what is the effect when there is no pre-stress, when there is an axial pre-stressing force 200 kilonewton is applied, and then when I have a curved cable profile. Remember, when you have a curved cable profile only, this Vp will come, which is equal to P into sin alpha, right. If there is no vertical force, this alpha is going to be 0. So, your Vp component is going to be 0. And in case D, we are going to look at when the beam is additionally pre-stressed by vertical cable. Now, I am putting a vertical cable and a stress of 2.5 megapascal in the direction. So, let us compare all these 4 cases and see how the principal tension is getting developed. Now, what are the given area? Cross section area is 100 by 300, which is 30,000 millimeter square. Moment of inertia is nothing but your BH cube by 12. You substitute, you get this value, and shear force is W into L by 2, which is 40 kilonewton, and shear stress, you know that it is 40 into 10 to the power of 3 divided by cross section area will give me the stress of 1.33 megapascal. Let us take an average stress only. Okay. So, let us look at that. Now, what is the axial stress that we are having? We are applying a force of 200 kilonewton, which is 200 into 10 to the power of 3 divided by 30,000, which is 6.67 megapascal. So, 6.67 megapascal of compression that I have applied. Now, let us look at, we know how to calculate your principal stresses using geometry of Mohr circle. I can derive the simple expression for calculating the principal stresses. You can refer to your strength of materials or solid mechanics book, and this is for any given element. If you know Fx, Fy and shear that is acting, then using this I can calculate both principal compression and principal tension stresses, right. So, let us look at now what is happening. For case A, if you remember, there is no axial load and I am looking at the critical cross section. So, if you substitute in this equation, right, Fx equal to 0 and Fy equal to 0, then principal stresses will be nothing but half of square root of 4 tau square, right. So, basically that will work out to be that, and if you substitute that, principal tension is working out to be 1.33 megapascal. So, here I am taking tension as negative. Okay. So, this is in tension. Now, let us look at what happens when you have axial pre-stress of 200 kilonewton. So, if you look at it here in this element, I am looking at it only this case. Okay. So, this only tau is acting. Now, in this case, if you look at it, I am taking this element, which is also not only having this, in addition to that, I also have an axial stress, which is Fx, which is equal to some value. This is also tau, right. Both are acting. So, that is what we are looking at. So, if you look at it, substitute Fx value and Fy is 0, okay, and Fx we have already calculated that, which is 6.67. So, if you put Fy and tau value is 1.3, substitute that, you will find your principal tension stresses 0.25 megapascal. Now, you see here the first case without any pre-stress had a tensile principal tensile stress of 1.33 megapascal. The moment I put my compression, that principal tension stress has reduced from 1.33 to 0.25 megapascal. So, that we can tell that prestressing helps in reducing the principal tension that is happening because of the shear, right. So, reduction is going to be quite significant. You see that almost 80% reduction is happening. Now, let us look at the third case. Okay. The third case, as you know, there is a curved prestressing which is force of 200 kilonewton. Now, from this again, you see here there is a slope of the cable, right. So, I am going to have this kind of a cable profile. So, if I take the small element, that is what we said, I am going to have this kind of compression, right, sorry. If I take a small element, okay, let me draw it right here. Okay. So, there is always going to be a vertical component. So, depending upon which section that I am taking, I have to calculate the slope of the cable, okay, and I calculated, let us say the eccentricity is taken as 100 mm and length is 10 meter. So, I know the slope of the cable is 0.04 radians at this location, right. So, now what is the Vp? Vp is nothing but P into theta or P into sin theta. When theta becomes small, then sin theta can be approximated as theta. So, 200 into 0.04 becomes 8 kilonewton. So, you see here now the net shear, we have seen that compared to, because of the prestressing, whenever there is a slope, that is going to have a component that is going to reduce the net shear demand on the cross section. So, 40 was the original demand, has been reduced by 8 kilonewton, my demand is now only 32 kilonewton. Now, the tau remains 32 into 1000 divided by 30,000, which is 1.06 megapascal, and Fx now remains same 6.67. We apply the same formula, and if you substitute that, you get your principal tension stress as 0.16 megapascal. You see, first case we got 1.33. If I had only Fx, I got 0.25 megapascal in tension. Now, in the third case, because the Vp is there, that has reduced the net shear. Now, the Ft has further reduced to 0.16 megapascal. This is also in tension only, right. So, you see here there is a reduction of almost 87.51%. So, what we can infer from here? If I can have a cabled profile, I can effectively reduce the shear demand in the cross section for a prestress beam. So, that is what it is, right. Now, let us look at what happens for vertical prestressing. But the vertical prestressing is difficult to execute it, but let us look at what are the benefits. So, where does the vertical prestress? So, horizontal prestress gives me Fx, vertical prestress gives me Fy. Now, let us see what is that Fx and Fy effect. Now, Fx is 6.67. I said vertical prestressing Fy, I am applying 2.5 megapascal somehow in the vertical direction. So, that means Fy is going to be 2.5. So, again you apply the same formula and get your principal tension stress. You will find that the Ft, which is a minimum stress, is coming to be plus 2.1, which is basically in compression. That means, by applying both horizontal and vertical prestressing, now I have converted that element which was originally in tension into compression. Okay. So, there is no tension at all. So, what is that we can tell from here? So, observations are, when you compare the case A and case B, the stress, the principal stress reduced by 81%. When you compare case A and C, it further reduced by additional 7%. The third case, if you look at the compare case B and case C, now if you go back and see, case B was only horizontal prestress, right. Case C was, it was having a cable profile with a slope. So, if you look at case B and case, further it reduced. So, and in vertical prestressing, the tension in the section is completely eliminated. So, that is what the benefit with prestressing is. I can, by changing the cable profile and the amount of prestress, now I can have the cross section both in flexure as well as in shear completely to be in compression. So, that is the point what we are trying. Now, what are the shortcomings in vertical prestressing? So, in post tensioning, typically a large number of anchors will be required to do the tensioning, which is practically becomes very cumbersome, and loss due to anchorage slip also will be higher due to short cable, because typically the vertical prestressing is done only over the depth of the member, right. So, the anchorage slip losses also will be high when you are short cables. And in pre-tension systems, of course, the loop ends of the web stirrups typically are embedded in the top and bottom flanges. They are cast first, and then what they do is they are tensioned by jacking the flanges apart before casting the web. So, it is a kind of little cumbersome approach. In pre-tensioning also you can apply vertical prestressing, it is more involved. Okay. So, but theoretically what we are finding is, if you have Fx and Fy, that means prestressing in the horizontal and vertical direction, if you can generate, and then you can have more benefits in reducing the tension that is coming in the cross section, both from flexure point of view as well as from shear point of view. Now, let us look at the crack patterns. Now, in RCC, you see that depending upon how the beam is designed, you typically tend to have this very well nice distributed cracks, provided if they are designed well, and you have, as we have discussed here, it is a flexure dominant region, and here it is a shear dominant region. In between this region, which is a both flexure shear dominant region. That is the reason the cracks initially it will become like this and it will become convert. Initially there will be vertical crack and then they will become like this. Okay. So, this is in RCC. Now, what happens in pre-stress? In pre-stress, because the amount of reinforcement itself is less, typically what we will have is less number of cracks. And they are more widely spaced, and shear crack also, as we have discussed, typically with respect to horizontal, it will become very shallow, less than 45 degrees. So, this is the effect of pre-stressing. So, pre-stressing in general, if you can see, it leads to less number of cracks compared to RCC element, and the crack also is going to become more shallower compared to the horizontal axis compared to that of RCC B. Okay. So, now when you do the analysis for shear, we should also look at what are the different possible modes of failure. We can have shear tension failure. You can have shear tension failure. Typically what will happen is you will have this kind of cracks that will be forming, and then that vertical crack, the shear crack, will start going up and down. At this location, if the rebar is not having adequate bond, then at this interface, because of this crack opening, it will lead to splitting kind of failure. So, this is one type of failure mode if the bar is not having adequate anchorage and if the bond is not proper in those regions, then you will have this kind of a splitting failure. Now, you can also have another type of failure after cracking. If you have a very thin web elements, then close to the tip of the crack you can have localized crushing. If you apply too much pre-stress, then again also it is possible, which is called as shear compression failure. Now, this is a diagonal tension failure. Here you do not have any bond failure, entirely because of the shear, the crack forms through the entire depth of the member and it fails by diagonal tension, right. So, this is a more common mode in shear, more common mode in shear. Now, when you have a very thin webs and if you apply lot of pre-stress, then you may have failure due to principal compression also, right. Now, principal tension always crack will form, but then between the cracks you will have strut will be formed that will be subjected to huge compression, and if that element is very thin and the amount of pre-stress applied is very high, then your element can also fail in principal compression. Typically, we try to avoid this failure in design. So, we avoid this by making sections larger. Okay. So, to prevent this only, we always make sure that tau v has to be less than tau c max. Okay. There is a tau c max limit that is provided in the codes, design codes, only to prevent this web crushing failure. Okay. So, typically when you from number of research that what we have done at IIT Hyderabad also, a lot of work has been done on shear behavior of self-compacting concrete and ultra high performance concrete. So, we have found that diagonal shear tension failure, which is like this kind of failure mode is quite common. You know, a single crack forms and then it tries to split open the entire beam. So, this one critical crack basically governs the behavior, as is called web shear crack. Sometimes what happens is flexural crack will form, but then it can get converted itself into a flexural shear crack as well. So, in this case also I think it is more of a shear tension failure only, but in addition to that you also have a lot of these flexural cracks. So, all these things are there.